This is the SolarCool project, which deals with improving the performance and lifetime of solar photovoltaic technology. Solar PV is a very promising technology for decarbonising global electricity production. Including manufacture, solar PV generates only 40 grams carbon dioxide equivalent per kilowatt hour, which is an order of magnitude lower than conventional fossil fuels such as coal, biomass and natural gas. Recently there has been renewed interest in solar PV as a technology for large-scale energy production, as the price per watt has dropped below a critical threshold. Solar PV is now the cheapest way to generate electricity in some climates. For example, it is outbidding coal or natural gas for energy tenders in northern areas of India. Currently there is 600 gigawatts of solar capacity installed globally, and this is expected to increase to 1,000 gigawatts in 2025. Solar PV operates by converting energy directly from light to electricity. Only 20% of the light incident on the panel is converted to electricity, and the remaining 80% generates heat. This results in a large temperature rise at cell level, which is most pronounced at midday. This temperature rise has two main effects. The first effect is that there is an immediate reduction in the output efficiency due to the underlying physics of a PN junction. Regardless of the solar cell technology, this reduction can only be avoided by keeping the panel cool. The second is a long-term decrease in the efficiency over the 20-year lifespan of the panel due to a combination of degradation effects. As part of the concept phase, we have identified 5 key stakeholder groups. We have engaged directly with the following companies, with representation from each of the stakeholder groups. They have confirmed directly that reductions in panel performance due to elevated temperature is indeed an industry-wide concern. Our solution to this problem is to make a modification on the back of a standard solar panel which improves heat dissipation. In the lab experiment, we replaced the solar cell in a conventional solar panel geometry with an electrically controllable heat source. This thermal image shows 2 identical test panels, one with our solution on the right and one without our solution on the left, clearly demonstrating a large difference in surface temperature. By controlling the heat source, we can investigate performance as a function of heat source density from 50 watts per meter squared to 800 watts per meter squared. The symbols in this graph are experimental data points, and the solid lines are results from full 3D numerical finite element method simulations we performed. This agreement demonstrates that we have a high level of understanding of the process. For the outdoor test, we fitted our solution to the back of a standard 50 watt panel. We directly compared the temperature and performance of 2 identical panels with and without the solution. Using standard industry test instrumentation, we can extract the IV curves and calculate the panel output power under a matched load. The histogram shows that there is a statistically significant improvement in output power by 19.4% under these test conditions. So what would the impact of our technology be? By taking global data on solar irradiance and background temperature from PVGIS, a database commonly used by the industry and maintained by the European Commission, we can calculate directly the annual increase in energy output that our technology would produce. The improvements vary depending on time of year, but we can see that the average energy output increases by up to 9% annually in arid regions and can still be above 5% in Northern Europe. These percentage increases are considered very large by our stakeholders. In addition to increased efficiency, we expect our technology will increase panel lifetime beyond 40 years. This would effectively further decrease the carbon footprint of solar PV below 20 grams CO2 equivalent per kilowatt hour. In order to develop our technology further, we have put together a team of scientists, engineers, industry partners and NGO partners that will maximise our chances to succeed. Our impact partners are Phelan Energy Group and Concern Worldwide, who are both active in developing countries and will provide guidance and support for the project. Phelan Energy Group are an Irish-owned company that own and operate a number of large solar farms globally in countries including South Africa and India. Concern Worldwide are a global NGO and will help us ensure our technology will be relevant for increasing quality of life in developing countries. Our goal for the seed phase is to demonstrate this technology on a scale relevant for solar farms. We will optimise our design and deploy field prototypes in Ireland and South Africa. Our impact partner Phelan Energy Group will give us access to their solar farm in Dar, South Africa. This is the largest solar farm in sub-Saharan Africa and will allow us to definitively prove our technology performance in the harshest of test environments. Our technology has the ability to provide broad global societal impact. Reducing the cost of solar PV will increase its uptake in the energy mix. This will result in a lower cost of electricity for the end consumer, improved energy independence and resilience, and a cleaner environment. Developing countries such as those in sub-Saharan Africa have particularly high solar resource, and solar PV is predicted to account for 9% of new capacity additions in the coming years. Now is the time to make a modification to this technology to increase its performance and lifetime, making solar PV into an energy asset for future generations, not a liability.